There's the most amazing thing in the universe, which is known to be dark matter. It is one of the most enigmatic concepts in modern science. We can see the importance and effects of its presence everywhere on a large cosmic scale. From low-mass galaxies to the largest galaxy clusters, from the cosmic microwave background to the cosmic web that traces the universe's structure. Let's know more. Hey guys, welcome back to our channel, Elon Musk Evolution, where we tell you all the latest news about Elon Musk and his multi-billion-dollar companies. In today's video, we are going to tell you about Elon Musk's belief that in order to travel interstellar, we need to develop a rocket that makes use of dark matter, which accounts for about 85% of all matter in the universe. Is dark matter, on the other hand, real? Let's dig deep. But before we get started, make sure you subscribe to our channel and hit the bell icon so you don't miss any of our incredible videos. According to Musk, technically, you can't go faster than the speed of light, but space can. However, the amount of energy required to warp space is enormous, so you'd have to be converting matter to energy at a rate that we can't fathom. There are 5 times as much dark matter as normal matter for every proton's mass, outmassing and outgravitating the conventional stuff that makes up everything we've ever directly detected. Even though we have yet to directly detect it, and we don't know exactly what its true properties are, dark matter holds enormous promise for humanity's future. Dark matter, which is widely distributed throughout the galaxy and beyond, could be the ideal fuel for realizing our interstellar ambitions. Here's how it happened. When humanity sets its sights on exploring the depths of space, there are some limitations we can't ignore. Physics law. To accelerate a spacecraft, or any mass for that matter, you must give it an impulse to change its momentum. The greater the impulse, the more you can change the speed of the object. All that determines the magnitude of an impulse is the amount of force applied, and the length of time it is applied for. That impulse is provided by rocket fuel, which undergoes a combustion reaction to produce an impulse in the form of thrust in a conventional rocket. Although this is the best method for space travel that humanity has devised thus far, it is extremely limited. Unfortunately, all of our previous and current rockets are chemical-based, which limits how far we've been able to travel. The reason for this is simple. In order to produce thrust, that is, to give your spacecraft an impulse, you must convert the stored chemical energy in the fuel into kinetic energy that propels your spacecraft forward. However, in order to generate that energy, you must expend some of the fuel you're carrying. Fuel efficiency is the key to getting a lot of thrust, and thus a lot of acceleration. Certain types of fuel are more energy efficient than others, implying that we can get more energy as well as thrust and acceleration from a given kilogram of fuel. Einstein's most famous equation, E equals mc squared, is a simple way to think about this. If you had the perfect ideal fuel, it would convert 100% of its mass into energy, allowing you to create the most efficient fuel possible. But let's just say what dark matter really is. Fritz Zwicky, an astronomer in 1933, noticed something was missing from the universe. When Zwicky was looking at galaxy clusters, he noticed that the total mass of matter was greater than what could be seen directly. Based on the motions of the galaxies near the cluster's edge, he calculated the difference between visible and invisible matter. Zwicky then noticed a distinction between the matter he had calculated based on the number of galaxies and their brightness, and the matter he could see directly. The motion of stars and galaxies, as well as the bending of light in the universe, provide 2 pieces of evidence for dark matter, according to Priyamvada Natarajan, an astronomy professor at Yale University. Because gravitational force dictates the motion of stars and galaxies, both of these reflect gravitational force, Natarajan tells Inverse. As a result, the matter you see should be proportional to the motions detected because gravity is provided by them. If all you see is what provides gravity, then it's consistent with motion, which isn't the case, says the author. As a result, some form of mass must exist between cosmic bodies, holding them in place via gravitational force alone. Zwicky coined the term dark matter to describe the missing mass. Despite 2 decades of investigations, the true nature of dark energy continues to elude us. Regrettably, most attempts to explain dark energy fail to pass stringent particle physics tests. However, new research demonstrates how a hypothetical form of dark energy could be created inside the Sun and detected on Earth. It's possible that we've already seen it. The most straightforward explanation for dark energy is that it is a cosmological constant, a numerical addition to Einstein's general theory of relativity. In other words, according to this theory, the universe expands faster because the universe expands faster, which isn't exactly a satisfying explanation. Physicists have attempted to link this cosmological constant to the quantum vacuum energy that exists throughout space-time, but their calculations predict an accelerated expansion strength that is 120 orders of magnitude too large. As a result, it's possible that dark energy isn't directly embedded in space-time. Maybe there's a new force, field, or particle at work in the universe that the standard model of particle physics hasn't discovered yet. This entity would explain the rapid expansion, but theoretical models have problems with it as well. The problem is, once you add a new force, field, or particle to the mix of cosmic ingredients, that force, field, or particle will begin to interact with all of the other forces, fields, and particles that physics knows about. That doesn't seem like a variable option because none of our high-energy, let alone low-energy physics experiments have revealed any new physics. Perhaps dark energy has another ruse up its sleeve. Perhaps there is some entity at large cosmological scales that causes the accelerated expansion, and something within that entity prevents it from interacting with known physics at small solar system scales. It's a stretch, but given that we have no idea what causes dark energy, it's worth looking into. But how do we find something that is designed to be hidden from our experiments in our experiments? Some theories believe that dark energy is caused by a novel type of particle, because it would have been produced in large quantities in the center of the sun, where densities and temperatures are high enough for interactions between dark energy and the standard model to occur. This hypothetical particle would not be able to interact with other particles from the standard model like electrons and top quarks. Inside the sun, the production of dark energy particles would disrupt its thermal equilibrium, affecting its light output, temperature, and lifespan. According to those theories, the sun can't be producing dark energy particles in its core because its behavior matches exactly what we expect from the standard model. However, a recent paper suggests another possibility. Dark energy may not be directly connected to any standard model particles, but it may be connected to photons. The tachocline is a region deep inside the sun where the sun's magnetic field is extremely strong. Photons carry magnetic fields, so tons of photons are produced in the tachocline. If dark energy is linked to photons in some way, dark energy particles may be produced here as well. The Earth's crust functions as a massive dark matter detector. A photon or neutrons can be knocked loose when stray dark matter particles collide with normal matter inside a rock, changing the chemical composition of the rock near the impact site. This may even send the particle flying, leaving a microscopic scar behind. Deep digs also have access to portions of the Earth's crust that are over twice as deep as our current dark matter detectors, promising results that are free of cosmic rays and other nuisance particles. And because rocks last millions, if not hundreds of millions of years, they've been recording dark matter interactions for much longer than we'll ever be able to access during the lifetime of our experiments. So here's how it works. Dig up some rock, preferably pure, so it'll be easy to analyze and examine it with a fine-tooth microscope comb for any signs of subatomic violence. We sincerely hope you enjoyed the video. If so, give it a like and share it with your friends and family. Let us know if you have any questions or comments in this section below. Don't forget to subscribe to our YouTube channel to see more of our incredible videos. You can also watch our other videos that have been specially selected for you.